So welcome everyone. Tonight we're going to discuss Schmidt Cassegrain telescopes for Cubesats. And most of you are familiar with what a Schmidt Cassegrain telescope is. These are very much smaller because they need to fit in a tiny cubical satellite that gets rideshare launched. This is how, if you're a high school or a college, you can afford to have a SpaceX or somebody like that launch your little educational experimental satellite. And they're really small. They're only about 4 inches by 4 inches by 4 inches. So if you want to put a telescope in there because you've got a camera and you want to take pictures of the Earth from your CubeSat, it needs to be a really small telescope. And that's what we're going to discuss, is those really tiny Schmidt Cassegrains for CubeSats. And they're made by one guy over in Europe, and he makes them by hand. But first, we'll talk about the news. Let me find the right mouse here. So much as I commented on last week, Hubble is stuck in safe mode and has been that way since the middle of October. They showed a few images from several years ago without making it obvious that they weren't current images, and people thought, oh, Hubble's back in operation. No, it's not. This time it's data synchronization. If you want an analogy for it, the best way to describe it is if you are doing astronomy using a USB webcam and the camera wants to send you data faster than your computer can process it, you'll drop frames, you'll lose synchronization with the camera, and you'll have to disconnect and reconnect with the camera and sync back up again once you lost sync. Well, apparently that's what's happening. The mission control computer on board Hubble is losing sync with the instruments. Anyway, in order to test out various solutions to this, what the NASA and Space Telescope Science Institute did was they turned on an instrument that was not producing adequate responses, good images. It's actually an infrared spectrometer aboard Hubble, and they haven't used it for more than 10 years. And in order to test out synchronization between the instruments and the mission administration computer, they've reactivated this camera. It's called NICMOS. It is the Near Infrared Camera and Multi-Object Spectrometer. They turned it off a while back because it just wasn't getting the level of information that they were looking for, so they turned it off. But if something has really gone wrong with the instruments and they're losing sync with the Hubble administration computer in the telescope, then an instrument that's been turned off a long time and suddenly turned back on would likely not experience the same flaws. And if they have to try out some new software, it's better to try it out on a known instrument that's not critical to current science. So they're playing with NICMOS. We'll give them a couple of weeks and see what they do. So I don't know if you've been following the ongoing saga of delays of the next Crew Dragon SpaceX flight up to the International Space Station. First, they had a technical problem. Then they had a, not emergency, but a medical condition with one of the crew astronauts. And now they've got weather again. This is weather at the launch site, I believe. So if you look at the mission duration of the NASA astronauts that are already on board the ISS, they're coming to the end of their mission duration. So they can't wait for the next crew to come up in order to do a face-to-face hands-off from one crew to the next. So what's going to happen is the current NASA crew is going to come back down, and then the new NASA crew is going to go up. But I think they're not separated far enough apart for the current crew to actually land, debrief, and then go over and meet up with the next crew before they launch. So there'll be a gap between the two crews. It's not a complete gap because there will still be 3 astronauts on board the ISS, 2 Russian and 1 NASA. So I should say 2 cosmonauts and 1 astronaut. The 1 astronaut that's there, he's on like a 6-month plus duration mission. He's one of the long term guinea pigs. So there will be some overlap between the new crew and this one NASA astronaut that will be still up there. And if you're comparing it to Jeff Bezos's launch gantry, look at that. Isn't that nice? It looks kind of like an airline passenger gangplank. It's fully enclosed. It's air conditioned. They actually have a covering bag on the front, just like an airplane gantry arm. The bellows goes all the way down up against the capsule. So very nice.
Yeah, very nice.
Yeah, they spend for the items people just expect. So both Perseverance and Ingenuity on Mars are heading back to very close to their landing site. They've sort of gone out to this edge of Jezero crater and done what exploring they're going to do there. Now they're going to come back to near their landing site and go out the other direction. I guess it's out the bottom here, because they're not going to go over this rough terrain. You can see how they avoided it. So they'll go out the bottom and look through another part of Jezero crater. But before they did, they marked a rock that they want to come back to. Looky, folks, on Mars, sedimentary rock. You can see the layers here. And once again, that provides evidence that liquid water on Mars existed for a long period of time, and it left Mars slowly in phases, is the best way to describe it. So the water went down a certain amount and then dried out, and it created a sedimentary layer. And then you had another period of time where the water stayed and then eventually went down. So this kind of sedimentary geologic action is quite normal on Earth. But they were looking for this same thing on Mars, and they found it.
Why did the water disappear?
Two reasons.
The loss of magnetosphere.
Two reasons. One is Mars is much smaller than Earth, so it has less gravity. So water vapor will more easily escape into space. And the second thing is the magnetic field of Mars is far less than that of Earth. So over time, the solar wind will strip off the upper atmospheric water vapor. So it'll eventually dry out. But it takes millions and millions of years to do so. And it looks like there were periods of time where there was water, and then it stripped away, brought it down to a lower level. And then it stayed for another few million years, and then it stripped it down again. So it looks like it's in phases, which if our sun were a red dwarf star, I would say these are the bursts coming out of a red star. But our sun is a dwarf, but it's not a red dwarf. So seeing this kind of thing on a planet as small as Mars with a small magnetic field says, I wonder what made it depart in stages. And you can see them getting thinner and thinner and thinner. It started out wide and then went thin. Now, if Mars had tectonic plate activity, I would say, well, maybe we're looking at something false here and the rock has actually turned 90 degrees. But since Mars doesn't have the same tectonic plate activity, if the rock started vertical, the rock would stay vertical.
How can a sedimentary rock be formed vertically?
It can't.
They do form firstly horizontally, and then as the tectonic plates activities and volcanic activities, you have the folding of the land, and then as you fold, you can change the orientation of the layers.
Think about rock that subsides below the surface. As it's bending down to go beneath the fault line, it will turn from horizontal to 45 degrees and then vertical. And if you catch it when it's vertical, the layers will be vertical. But in the case of Mars, there's no known tectonic plate activity. So if it forms sedimentary layers horizontally, we're not looking at an aberration here. They really formed horizontally.
All sedimentary rock forms horizontally and then turns vertical, doesn't it?
Yes, not always, but you have to imagine that land is almost like a fabric. So you have tectonic plates making pressure. So something that is flat, you can actually have mountain formation or subduction zones then you have those layers that make like, you know, a fabric that's being folded. So it's some of the orientation goes down, some of the orientation goes up, some on the top or on the bottom of the truss, and they become flat again. So they change orientation because of the folding of the continents. So if you take a look at areas that you have subduction zones, or you have those continents colliding, if you look at the aerial picture of it, you can actually notice that it almost looks like a fabric that you crunch it up. You can actually see the folding, and you can observe that where the forces are coming from. So you have an area that doesn't move much, and the other area that actually collects the material because there are forces pushing the fabric together. So just think about land. When you have an earthquake or when you have tectonic forces, land almost works like a fluid.
But you're correct, Adam. It does form horizontally and then gets tilted in the presence of tectonic plate activity. But since there's no tectonic plate activity that we know of on Mars, it formed horizontally and it stayed horizontal.
So Sarah is going to the Rift Valley in Kenya this summer to work.
Cool.
Yeah, they're like reconstructing Cenozoic environments with sediment, something or other.
That is awesome.
Okay, so this next story is about the Decadal Survey on Astronomy and Astrophysics from 2020. Every 10 years, the National Academies of Sciences, Engineering, and Medicine of the US government says, what are we going to study next? Which is the clue to the US House of Representatives. Where do you want to spend money in the next 10 years? And so I was waiting for this survey to get done. It's actually the 2020 survey, but for a variety of reasons, they didn't finalize it last year. They're updating it this year. So the update came out on November 4th. And the interesting thing that I noted right away was that, hey, they're putting money back in radio astronomy. So rather than trying to tear down places like Green Bank and the VLA or mothball them and, basically writing off Arecibo, they're going to be spending a lot of money over the next 10 years at the next generation VLA, going to be an array of 263 dish antennas. They seem to be not as big as the current VLA dishes, but it looks like they'll be cheaper to make. They look very similar to the Allen Array, the SETI Allen Array telescopes, but they're a little bit larger. So the NGVLA looks like it may be in for some money. I didn't read the rest of the survey, so I don't know if they're going to be spending money on our next generation 2 deep space telescopes, the very much larger than Webb telescopes. But there were 2 projects that were in there. I'll have to see if they passed the survey. And this was something that I guess more than a month ago when we were discussing gravitational wave detection. And there was the point that low frequency gravity waves could not be detected by LIGO. It takes a different kind of instrument, a different level of sensitivity, a different baseline length. Instead of it being 4 mile long, it had to be many thousands of miles long. Well, they're going to make it many light years long. If a millisecond pulsar is highly accurate because the neutron star is spinning so fast and putting out energy, then you can time the accuracy of the spinning pulsar down to a small fraction of a second. If you do that for a large number of pulsars, you create what is known as a pulsar timing array. If any of the pulsars beam makes it to Earth, not at the precise time at which it was predicted, but a slightly altered time, it arrives sooner or later than expected. And you get that not out of a single pulsar in the array, but several pulsars in a portion of the array, and they're all offset, in the same direction, then that means that fabric of space-time between the Earth and those particular pulsars has expanded or contracted, which could probably be due to low frequency gravity waves or very, very large area. So it'll be interesting to see what they do with that. But I don't know that you have to wait for any US federal funding for this, because it's actually being funded by Italy. They have their own test program, and they're, you know, they don't have to create a lot of stuff on the ground. They just have to have a few detectors to pick up the pulsars. So they need a few reasonably capable radio telescopes to examine several pulsars at the same time. And yes, tomorrow we go off of Eastern Daylight Time back on to Eastern Standard Time. And let's see. There will be no session, no online session this coming Saturday, November 13th. Ellen and I will be going to a friend of mine's second daughter's wedding. So we'll be doing that. The following week on November 20th, we'll be discussing how to get rid of Earth orbiting space junk. If you remember when we were talking about constellation satellites, I sort of postulated this approach of, well, maybe we can put a laser at a high orbit above all the geostationary, and then use that as kind of a laser solar sail effect on all of the lower down junk, and push it down until it you know, drags into the Earth's atmosphere and it burns up. As you could tell, I'm playing with the astronomy camera again, and I've started writing the drivers. I've got maybe 25% of the driver code done. I have to actually write 3 drivers. I have to write one for the telescope, basically the mount of the camera, another one for the imaging part of the camera, and it can do snapshots as well as live video streamings, capture those. And then I have to do one for the focusing, because that's how astronomy applications expect the telescope to be controlled and the camera to be controlled. I don't have a topic for December 4th. December 11th will be our James Webb Space Telescope with our subject matter expert, Will, from the Space Telescope Science Institute. And then on the 18th, I'm not going to plan a presentation. It may be short, but we'll just give an update on the hopefully successful and timely launching of the Webb and its in progress unfurling status. I do have something for us to discuss at this point before we get into the presentation. The 2 weeks following that are Saturday, December 25th, which is Christmas Day, and Saturday, January 1st, which is New Year's Day. I'm a flip of a coin on this as to whether we should do these sessions or not. Anybody have an opinion of not doing them? Would anybody have a problem if I canceled those 2 sessions?
No,
No.
No,
Okay.
cancel if you
Okay.
like.
we'll probably be in turkey overdose.
Well, that's the day they track Santa Claus, don't they?
Yeah.
No, they track him on the 24th,
Oh, yes.
the Friday before, when he's actually up there flying around delivering stuff.
You know, it would be interesting to track him on the 25th.
If you could find him on the 20th, he's probably home asleep.
Yeah.
Too many cookies.
Okay, so
Uh-huh.
when I put out this week's video to the YouTube site, I'll post that we're not going to have a session on the 25th or the 1st.
Yeah. Holidays.
So welcome. Tonight we're going to talk about Schmidt Cassegrain telescopes for Cubesats. I'll explain both what a Schmidt Cassegrain telescope is and what a Cubesat is. So a Schmidt Cassegrain telescope is a type of what is known as a catadioptric or multiple component reflector telescope. It involves a spherical corrector known as a Schmidt corrector plate, the primary mirror, and a secondary mirror. The light comes through the front, goes out a hole in the back after bouncing off the secondary. That design has a good balance of magnification with minimal optical aberrations or distortions. Given that the surfaces are spherical, they're easier to grind than, let's say, a Maksutov Cassegrain, which has a meniscus for the corrector plate. A CubeSat is a standardized form factor. In other words, a standard dimensions, weight, power, etc. for a small, uncrewed, it sounds weird to say uncrewed. It sounds like I'm saying it's horrible, as opposed to saying there's no people on board. It's an uncrewed satellite base level design. CubeSats are inexpensive to build and test, and you can generally pack a bunch of these onto a single rocket launch. So you can do what is known as ride sharing. So instead of the cost of your satellite launch exclusive for your one satellite being like 100 million, or ride sharing with a your own design satellite at 20 million. If you design it with CubeSat specifications, it's probably only $1 million. And if you can get a university grant or an educational grant, it's probably only a couple $100,000. So that's the scale we're talking about, is in the couple $100,000 to build it, test it, have it certified and launched, which is a lot of money, but it's a lot less than the 100+ million. So here's a Schmidt Cassegrain telescope. You can see that the light comes in here. Oh, a laser beam. The light comes in here on the right, goes through the corrector plate or the Schmidt plate, bounces off of the primary mirror at the back, bounces up to a secondary mirror at the front behind the corrector plate, and then goes out through the hole, the Cassegrain hole in the back of the telescope to the camera or eyepiece. Now, because we have this corrector plate, instead of the primary mirror being parabolic, it can be spherical, because as you can see, this lens effect on the corrector plate bends the light so that now all of the light can make it onto a single point of reflection, which is out here, but they put a secondary mirror in its place, and you have a convex spherical secondary mirror. So it's also easy to grind, and that bounces the light back.
Okay, I heard parabolic. I don't know what that means. Thank you.
It's from geometry. It's a parabola. A parabola is a kind of curved shape that if you were to, well, the best way to describe a parabola is if you were firing a cannon and you fire the cannon not quite vertical, you fire it just a little past vertical, the curve that the cannonball takes going up and then back down to the earth, that particular kind of curve is a form of a parabola. And as you make the cannon tilt down further to fire longer range, it's all still a parabola. But the problem with the problem with a parabola for a telescope mirror is you can't readily grind it with a single grinding shape instrument, because the outer edges actually bend up farther than the center. But with a spherical, as in sphere, you can make one grinding tool that can cover the entire range of the mirror or the lens, and you don't have a fancy shape to worry about. It's cheaper and easier and faster to grind them. So that's why you want your reflector telescope to have a spherical, non-parabolic mirror.
Thank you.
Okay. Cassegrain is the guy's name, and it just refers to the hole in the center of the mirror where the light comes out. Schmidt is also the name of a guy. He's the guy that came up with this plate that is a corrector plate that allows you to have cheaper parabolic mirrors. The secondary mirror is convex, so that's easy to build. But the Schmidt plate itself is actually hyperbolic. So if you take a parabola, it has one hump in it, one bump. If you were to spread that across and have two bumps, that's a hyperbola. Has nothing to do with hyperbole. That's just a more complex curved shape. And you can see it here. There's one dip, and then it comes back up, and then there's another dip. And you do that circularly around the corrector plate, and that's how you shape your corrector plate. Now this is two parabolas. If you were to make a Maksutov Cassegrain corrector plate, it actually puts the curve, instead of going up on the end, it goes back down on the end. It's what is known as a meniscus. And a meniscus is the shape that you get if you have a test tube full of water and you don't fill the test tube all the way up, you fill it about halfway. The curve of the water, given its surface tension against the glass of the tube, that dip you see in the top surface of the water, that's a meniscus. Which explains why a Maksutov Cassegrain telescope costs a little bit more than a Schmidt Cassegrain. Oh, but they're also better. And here's a CubeSat. It looks like a cube. They don't necessarily have to look like a cube. This is what is known as a 1 unit or a 1U CubeSat. It's 100 millimeters by 100 millimeters by 110 millimeters. So it's almost a perfect cube. But it's basically 4 inches by 4 inches by about 4.3. Now, what's the 0.3? That's these mounting posts. That has to be taken into account. So the actual satellite itself is still 4 by 4 by 4. Everything about your satellite, its electronics, its radios, its antennas, its solar panels, its batteries, everything has to fit inside there. And the maximum mass, the maximum weight on Earth of your CubeSat for a 1U CubeSat is 1.5 kilograms or about 3.3 pounds. So if this is the inexpensive rideshare satellite that you're attempting to create, it's obvious you don't have room for a large telescope. This is actually a model of a satellite that was launched. It's called DragonSat. So they give them a cute name, DragonSat. But the one we're going to talk about is one from an educational institution in the US state of Oregon. So it's called ORISAT. So traditional Schmidt Cassegrain telescopes are not known for being small in aperture or length. They like to be large enough to gather lots of light. So typically a bottom end SCT would be about 8 inches. I think you can get some at 6 or less, but they're kind of outliers. And a typical 8-inch Schmidt Cassegrain telescope, it comes with a mount and a tripod and electronics and a hand controller and all that stuff. And it starts at about $1,000. Obviously, if you're going to make a Schmidt Cassegrain telescope fit within a 1U CubeSat, it's got to be smaller and cheaper. If you think about light gathering, you want a larger diameter telescope so you have more light gathering for dim, deep sky, fuzzy stuff. But in the case of a CubeSat, you're likely pointing your CubeSat down at the Earth. And so if you take your imagery during the daytime, then there's a lot of light coming up from Earth, so you don't need a lot of diameter. And what you want is sufficient magnification, courtesy of the focal length to focal ratio of your Schmidt Cassegrain telescope inside your CubeSat, that you'll get the magnification you want without it being enormous. But CubeSats are not made in high volume. They're made kind of one at a time production. So if you're going to have a Schmidt Cassegrain telescope in your CubeSat, you're not going to have a high volume production for it. So it's not going to be mass manufactured. It's going to be what they call artisan or bespoke telescopes. And they're going to be smaller, but you need them at a lower price because you're putting them in shared ride CubeSats from educational institutions. So this was something that Helen pointed me to, and we briefly spoke about it in a session a couple of weeks ago. This is the entire telescope. It's ground by one guy.
I laughed. That's a whole telescope.
That's the whole telescope. It's ground by one guy by hand. This one does not have the reflective coating on the primary yet. But you can tell from his fingers, it's around 1 inch in diameter and about 1 inch length. You can see the secondary reflective surface right here. It looks like there's a lens stuck on the front of it. And then you can see the hole, the Cassegrain hole that goes out the back. And you can see they've put a black coating on that. That acts like the baffle tube to make stray light, not make it down through your Cassegrain hole. And then the outer surface of the telescope is also coated to remove stray light. So the light would come in through the corrector plate, bounce off the primary mirror at the back, bounce up to the secondary, and then go out through the baffle tube shrouded Cassegrain hole out the back. So there are no
Extremely
structures
clever.
there's no structures to hold it together. It's ground from a single piece of glass. And he uses
I find it so clever. I found it genius. When I saw it, it was like, whoa, nobody thought this before. It was so obvious. It is really brilliant.
so here's how you grind one of those. Here's the steps. I watched the video, I looked at the information, and this is how you make a Schmidt Cassegrain telescope small enough to fit inside of a CubeSat. You take a single glass blank. It's a circular, it's a tube. It's a circular blank. And then you're going to grind 3 separate surfaces for it. So you're going to have a spherical corrector plate onto the front. You're going to have a spherical secondary that you grind into the front. Then you're going to have a spherical primary on the back. And then you drill a hole through the center. Hopefully you're using a very accurate computer-controlled drill to drill that precise hole. And then you start putting coatings on it. You put a dark coating on the inside of the baffle tube. You coat the back of the secondary with a reflective coating. You coat the back of the primary with a reflective coating, and you coat the exterior of the glass blank to keep out stray light. And that's all it takes. So here's the artisanal bespoke production. The guy's name is Richter Horst. He works at Nova Astron. That's an abbreviation. I guess it's Nova Astronomy in Northern Europe. He first made one of these in 1993. And since he's grinding these by hand and the surface quality takes priority over the exact specs of the telescope, you don't know what focal length telescope you're going to get or what focal ratio telescope you're going to get until he's done grinding. Because if he grinds and he sees there's a little flaw or it picked a little too much of the glass, he's got to grind it down further to get rid of that. So that changes the spec of the telescope, but that's the nature of grinding a telescope by hand. Depending upon his available time and how well things are going, it can take 1 week to several weeks for the initial grinding. And then he has to do a quality test on all the surfaces, and only then do they apply the coatings. And up until they apply the coatings, they don't actually know what the true focal length and focal ratio of the telescope will be. But because it's a Cassegrain, you can put corrective lenses on the backside of the Cassegrain hole to adjust for if the focal length isn't what you want, if the field of view isn't what you want. You can either expand with the opposite of a Barlow lens kind of thing. You can have a focal reducer, or you can have a Barlow to give you more or less magnification as an after the fact lens. And those lenses are just standard, convex on both sides kind of lenses. So not knowing what you're going to get until it's done means you have to work on your actual imaging optics after the lens is done. The remaining downside is that if this guy's busy and you're number 2 in the list, it could take months for you to get your telescope. And you have to have a friend of a friend recommended to him in order for him to take up the task of grinding your telescope. So I took a look at some of the optical characteristics of what he was talking about. The aperture is typically 1 inch, so 25.4 millimeters. The focal length of these handmade telescopes, and here's the part about he starts out at one size, and when he gets done grinding, it can be smaller. He actually, just to see if he could do it, he made one that was 12 inches long, 300 millimeter. And he typically makes them at about 4.92 inches. So you can see he starts with a 5-inch blank and then starts grinding down. He may get less than that if things don't go well, but you're going to get a telescope that's somewhere between 4 inches and 12 inches. Exactly where, my guess is the majority of the ones that he produces are closer to a little less than 5 inches for focal length. The blank always being the same size, the diameter, your aperture is going to be the same. But if you're observing in the daytime, facing the Earth, there's plenty of light to gather, so a small aperture is fine. If you wanted to drive up demand, and as more 1U Cubesats get launched, now don't worry about how many of these things are getting launched. They're all launched into very low Earth orbiting altitudes, so they fall back fairly quickly. I think in a matter of months, they all fall back because they're just they're scientific research. Can we do this? Can we build it? It's for a high school or a university kind of, can we do this? Which is good for their career to get them onto building bigger satellites so they learn the ins and outs. But if they could reduce the price of this from closer to $1,000 than $1 million, then they might say, we need more of these and one guy making them is not enough. Or if the back-end optics become stock size for a 1U Cubesat, now you've got to have manufactured telescopes in order to make all the telescopes of the same specification. Now, how would you get the count up? Well, you can make rocket launches cheaper, you can make Cubesats cheaper, or you could start launching these telescopes on balloons, helium-filled balloons. You can launch a lot more of those at a lot cheaper cost than you can rockets. You could also put them on drones. So if you wanted a drone with a telescope on board to do better observing for whatever commercial purpose you've created it, this would be a good approach to creating those, but you're going to have to mass manufacture them. But if you think of it, that's the way telescopes have been. All the mirrors and lenses at one time were ground by hand by the individual who owned the telescope. Nowadays, not so much. So Schmidt Cassegrain telescopes are a great balance of optical design versus production costs because they can make spherical surfaces instead of more complex surfaces for the mirrors and lenses. Cubesats are small. They have standard specifications and everything must fit inside of it. There are other sizes of Cubesats. Instead of 1U, there's a 4U, which is the same 4 inches by 4 inches, but it's 12 inches long. So you can have a longer telescope in that, but that makes it a much more expensive Cubesat. Cubesats are not done in high volume, so you're not going to have mass manufacturing of them. And they can't cost a lot because universities and high schools use them. The artisanal, the bespoke SCTs are good because he can make them. Doesn't cost him a lot for the blanks. My guess is the schools cover the cost of the blanks and he donates his time. Because he has a day job with an optics company. But most of the optics that he makes are for grinding of cataract lenses. You would think those would be mass manufactured by now, but apparently not. So should there ever be sufficient demand, maybe, production grade small SCTs will be made. But the interesting thing is it's still a Schmidt Cassegrain. So the number of surfaces to be prepared is still the same. You've still got a corrector plate, a primary, and a secondary. But instead of a lot of structural parts to hold it all together and adjust it, it's just one chunk of glass. Has anybody noticed the odd thing about it? Because it's one chunk of glass, how do you focus it? You focus it by making the elements behind the telescope out the other side of the Schmidt Cassegrain hole, you move those back and forth. You don't move the primary mirror closer to or away from the secondary. I asked this question years ago about if a Schmidt Cassegrain telescope is so difficult to make mechanically, the bigger ones, because you have to have a giant heavy mirror that can move back and forth. Why not fix the mirror and move the optics at the back end? Well, this is proof that, yeah, that works.
Monroe,
Yes.
for heaven's sake, why don't you just print it on your 3D printer already?
I can't print glass yet.
Well, get
But
to work on it. Come on.
Well, I was actually looking at a video this week of 3D printing one of those little tugboats, a Benchy, and they printed it at, it looks like it's about 1/10 scale, and they used a 0.1 millimeter nozzle on the printer. And I've actually used a 0.1 millimeter nozzle on my 3D printer. You can produce what looks like skin. I mean, it's very flexible and it's thin and you can stretch it. So yeah, I can produce very small, very thin things, but they're not optically transparent. But what
Does it
I
have to be plastic? Can it be that? Well, what's that kind of plastic that you were talking about last week when we were discussing petroleum, the one that's made for optical devices? You know which one I mean. Can you
Yes.
can you 3D print that?
Polycarbonate, yes. Yes, as a matter of fact, you can 3D print polycarbonate filament. You would want it to obviously be larger diameter but higher temperature in order to smoothly print and have the layers adhere to one another. I'll have to,
Okay,
I'll have to do
remember
some
I gave
research.
you the idea. Just remember I gave you the idea, okay?
Okay. But what I was actually thinking about is going the other direction. If this is a small Schmidt Cassegrain telescope, can you make them even smaller? Now, this guy obviously is at the limit of hand movement on the grinding tools. This thing is only 1 inch in diameter, so he's working it like this. It's not a big blank that you can work on. But if you wanted to make them even smaller, you could, using this design, make a Schmidt Cassegrain telescope out of a silico aluminum blank, which is what they use for big professional telescopes. You can make a little tiny blank that might be, you know, 1/4 of an inch across, and you could use a helium beam etcher to actually grind the material away. And it can grind to 10 nanometers resolution. So it could grind the surfaces to whatever contour you want it because it's under computer control. And it could drill the hole for the Cassegrain and stop precisely where you want it without leaving a barrel bottom from the drill bit, which is something he didn't mention about his artisanal telescopes. Is if you run a drill bit down the center of the mirror in order to reach where the secondary mirror is, how do you get the bottom ground smooth? That was just that was an elephant in the room not mentioned. But I think you can make Schmidt Cassegrain telescopes using this technique out of appropriate materials really small. So if you wanted your Dragonfly drone to have very high magnification imaging capability, you could make a Schmidt Cassegrain telescope with helium ion beam etching. It would be very, very small. So here's some links, explanation of what a Schmidt Cassegrain is. It's on Wikipedia, you can find it. So can you find Maksutov Cassegrains, Cubesats, and you can look up Orasat. It's from the Portland State Aerospace Society. The other ones were the tiny Cubesat and DragonSat. And then the YouTube video of this guy actually making the tiny Schmidt Cassegrains by hand from a single piece of glass. It's fascinating to watch. It's not that long a video. I had understood that it was going to be a short topic this evening. I didn't think it was going to be this short. I thought I was going to blather more. So any questions about this presentation or the topic of Schmidt Cassegrain small telescopes?
This business about making tiny lenses has been interesting me. They've got them on laptops. They've got them in, cameras in your car.
Yes.
Very tiny little lenses, and they're clear and they're sharp.
Well, if you remember the advent of digital cameras, when film cameras existed, and there were 35 millimeter film cameras, and digital cameras were coming out with 14 millimeter lenses, and the comment was, digital cameras will always be crap. They'll never be as good as film cameras until they get a Filmback size CCD, chip, CMOS chip, that is as big as a 35 millimeter film frame. And there was a point at which Kodak actually made a film frame size digital imaging chip. And they made a back that you could substitute out for a Hasselblad. If you know about a Hasselblad large film back camera, they're good for taking landscape, for doing photographs for giant murals, because they capture a lot of detail. Well, Kodak made a film back for Hasselblad so you could do digital imagery. And what they found out was the digital imager was far more precise than film ever could be chemically. And the guys that had paid, thousands of dollars for their Hasselblad camera and their lenses started to notice distortions in the images. And it was inaccuracies in the molding and grinding of their very expensive lenses that they could never detect if they were using it with film. But the moment they started using it for high resolution digital imaging, they noticed these shadows and these swirls that would show up in their digital images. And much like amateur astronomers take flats, this is when you put a sheet over the front of your telescope and you shine a very bright white light into the front, then any distortions in the lenses or debris on your imaging chip will show up in the white image as a distortion. And then you can take a grayscale image of that and literally subtract it out of your final image as a microscopic change in the pixel levels, the pixel values. So what they started having to do with these Hasselblads was to take a flat in order to remove the distortions from their very expensive lenses. And then at some point, I don't know exactly what resolution, but at some point, the pixel size and the pixel light sensitivity just went off the charts. And the cameras on phones and laptops and such are now a small fraction of an inch, and they have enormous quantities of pixels, 20+ million pixels in the image. And so the concept of that'll never be as good as the analog stuff, analog film versus digital imaging. At some point, digital exceeds that, and the question just goes away. The critique just goes away. Cameras with high pixel counts and high resolution and high quality tiny glass lenses are now so inexpensive that instead of your mobile phone having one camera on it and then having a mechanical zoom that was under control of the camera to adjust the field of view and the zoom and the focus, that was the expensive part, the mechanical of the optical train. So now your camera just has 3 or 4 cameras on it.
Yeah,
And
yeah, True.
What kind of image do you want? I want a close-up. Well, it'll shoot with that camera instead of that camera or that camera. Or I want a low light image. It'll shoot with the camera that doesn't have an infrared cut filter on it. So the lenses and the cameras are now cheap enough. They just throw in a couple of them. And oh, by the way, it's not just 3 or 4, it's actually 4 or 5 because they have a camera on the front side for you to take your, personal video conferencing and selfies. So, things start out expensive until you start making many millions of them. And then they just get cheap because they're no longer artisanal. They're no longer bespoke. They're all mass manufactured by machines. And
the quality is so high.
Well, when you're just cranking them out like cookies and the machines and the grinding instruments are grinding at such a high resolution. I can remember when digital cameras first came out and they had, in order to reduce the price, they had plastic lenses in them. But after a while, the plastic lenses would get scratched or start to absorb some UV and get a little haze. And at some point, web cameras just said, let's just put glass lenses in everything. I'm guessing, the Cornings of the world or whoever makes all these glass lenses just up their manufacturing skill and precision, and they're just cranking them out like cookies. But yeah, just when you think the old guard is going to stick in there and always be better, if it's analog, digital just has to catch up. I watched a couple of videos today on YouTube about a company called BYD in China, and they used to make internal combustion engines. Then they made hybrids, which were half electric, half internal combustion, and then they started making electric. They are now making more electric vehicles and selling all that they can make. They're having to build bigger factories, and the number of plug-in hybrids and internal combustion engines or ICE vehicles that they're making is dropping by more than 10% per month. So at some point in the next 2 years or so, it's just not going to be cost effective for them to manufacture internal combustion engines or maybe even hybrids as well. And they're just going to make electrics. And the outfall of that is the job food chain of internal combustion engines could come to an abrupt halt. So much like all the people that used to make film for film cameras, not so much anymore. All the people that used to make film cameras, not so much anymore. All the people that used to make a dedicated, a Fuji or Kodak camera, as opposed to just something that comes with your phone, not so much anymore. Well, the same is about to take place with motor vehicles, because internal combustion is going the way of the horse and buggy, and electrics are coming in rapidly. You know that there's no shortage of demand when you build a factory that has a certain capacity and you're bumping your head at that capacity because you have more orders than you have manufacturing capacity. So you go spend $1 billion, and over the next 2 or 3 years, you build yourself another factory that is actually bigger. The problem is the existing internal combustion engine factories are so, I guess you could say, hinged by what they are building, and all the manual parts and manual operation of what they were building. You can't just kind of flip a coin and convert a factory from internal combustion engine to fully electric, because there's so much robotics you have to put in. The building itself becomes noise in the cost of setting up the rapid manufacturing chains. But that's just the way things are going. And I'm guessing that at some point, so many people are going to be laid off from internal combustion engine manufacturing and all the downstream. The people that make gas tanks, the people that change your oil. Electric vehicles don't need an oil change. all of those people will suddenly be shutting down businesses and looking for jobs. And the concept of, well, when that happens, what do? You don't want your economy to fall apart. So the concept of universal basic income, or UBI, rears its ugly head, because if you can't retrain people fast enough, and they're in the, they're in their middle of their career, at their 30s or 40s, you may not be able to migrate them onto making electric vehicles, because you don't need as many people to make the electric vehicles, because it's more automated. So that's a paradigm shift and a disruptor. I haven't done one of those on cars, but yeah, I watched a video of that more than a year ago, and they were talking about the number of jobs that are going to go away. Given that Tesla is now in the automobile insurance business, and they're selling the automobile insurance for Teslas at a noticeable discount over the major automobile insurance carriers, the State Farms and the Allstates and such, that it could be the big boys are going to get out of the automobile insurance business because there's too few customers, and the ones that are left are not the best of drivers. And it's going to cost more to repair an internal combustion vehicle when the parts come up scarce. So, the future.
The future
I know,
is now.
I'm always gloom and doom, ain't I?
Yeah.
Or what was it, the cartoon that said, "I'm a rascal, ain't I?" Bugs Bunny. Yeah.
That's what Elmer Fudd called him, a rascally rabbit.
Yes.
West.
Yes. Anyway, well, I remember what he said now. Ain't I a stinker? That's what he used to say when he would get caught doing something that the audience would go, "That's not right." He'd just look at the camera and do like a Stan Laurel and go, "Ain't I a stinker?" Anywho, any news items, other topics, improvements? I noticed that our last session, when I put it up on YouTube, was over 3 hours. So maybe this will get people watching again, because it's going to be an under 2 hour session, even including the news, by the time I edit it down. I did go back and look at the observing statistics, and for a couple of the videos, we've crossed 50 people watching them, but it's the ones with the clickbait titles involving EM drive and, stop looking for ET and things like that. So the clickbait titles work, but you'll only get so far with a 2+ or 3 hour video that people have to watch, because so many of the YouTube videos are 15 minutes or less that I have to go back and think about that additional YouTube channel I'm thinking of, where it will have the clickbait, short, pithy presentations. So this week I watched a video with Doc. I like to call him Doc Brown because it's so Back to the Future. The Dr. Brown is the PhD. Mike Brown is the PhD astrophysicist and astronomer that finds all of these things in the Kuiper Belt. And he's been using data from a variety of telescopes to narrow down where the 9th planet is. And he's gone from the whole sky to a swath of the sky to a segment of the sky. But it's still, degrees by degrees. But it is between Orion and Taurus at a width of about half the width of Orion. That rectangle is where he believes the 9th planet is going to be found. So, but he's already said it'll be too dim for amateurs to find it, much as he'd like to have amateurs get involved. It'll be too dim for amateurs. So in the Q&A, I sent him a question about, well, why not use radio astronomy? if the cosmic background radiation is supposed to be smooth and uniform, then if you have a planet the size of Neptune that has a magnetic field because it's that big, and it has an atmosphere that extends it out a certain distance beyond that, and it might have one or two natural satellites or moons that would be orbiting, all of that stuff would create a detectable drag effect in the cosmic background radiation. And so wouldn't it be easier to look at this thing without having to worry about how bright it would be of reflective sunlight? Because if it's covered in soot and it's so cold that its atmosphere is frozen to the surface, it's not going to be all that bright reflectively. And if you're looking for it to produce infrared heat, if it's that far out in space, it's going to be very, very cold, almost to the temperature of space itself. So it's not going to show up that much on infrared cameras. But you may get a drag streak in radio. And his apparent experience with radio astronomy is wide field. Doesn't have the resolution we're going to need. I guess he hasn't been acquainted with the fact that we radio imaged using an array of radio telescopes a black hole in another galaxy, which is so small that no optical telescope on this planet could have photographed it. So yeah, radio astronomy arrays can see big stuff and small stuff. It's just a matter of how you adjust the receivers. So that's the second time I've actually put that bug in his ear. And the second time he said, radio doesn't have the resolution for doing this. Okay.
But you would need like a array of telescopes that would be larger than the planet.
Why does it have to be larger than the planet? We already have one as large as the planet that saw a black hole, and the black hole arc, fraction of an arc second diameter was so small that no optical telescope could have seen that. So
yeah, but in that case, it would be a strong signal that's in radio. A planet has very little signal in radio.
I think Jupiter would counter that argument.
A faraway planet, it produces very little radio.
And you
because
think that
of the angular diameter.
You think that a black hole produces more radio because that was detectable. A black hole produces more radio than would a Neptune-sized planet in our solar system.
Yes, it does. Very strong signal.
Okay,
Especially if it's feeding.
With a single radio telescope of 125 meters in diameter, we are able to pick up the Voyager at the outer edge of our solar system, which is well into the Kuiper Belt.
But not as far as they predicting to get the number 9.
I would say let's not discount it out of hand before it's tried. Because I think that an Earth-sized radio telescope array has both the signal gathering capability as well as the angular resolution to pick up something the size of Neptune, even if it's 8 billion miles away. First, they have to have the faith to try it. What's that plaque outside Los Angeles Union Station? I've got it up here on my wall. It's at the base of the sundial. Vision to see, faith to believe, courage to do.
Nice.
Yeah. That's from 1937. Laverne Kirby came up with that. That was back when they were commemorating the Los Angeles Union train station. And they had a sundial and they wanted to put a plaque on it. And the city of Los Angeles wanted something to put on the plaque that would be memorable. So that's what's on the plaque. Okay, I think we're going to quit an hour early tonight.
Yes, because I'm not participating that much.
Good night, everyone.
Good night,
Good
y'all.
night.
I
Bye.
really enjoyed the
Bye, folks.
chat.